Okay, so I just want to revisit now the full velocity video and redraw the diagram that I was doing up here, kind of a bit small. After that, I've now properly introduced this proper time definition. So let me just remind you that we had, well, first of all, we defined the full velocity to be the derivative with respect to this proper time parameter of our world lines, which are just parameterized using this proper time. And we saw that this has a fairly nice representation. It's simply just a vector that points in space-time. It's effectively giving your tangent velocity to your world line. So it's going to have some time component. And remember, we introduced this gamma, the Lorentz factor. We're going to explore this a little bit more in upcoming videos. But now the full velocity, we have the time component, and then the space component, which depends on our coordinate velocity. And now we saw that there are three possible cases that the length of this full velocity can have. Essentially, the length can be 0, which corresponds to this coordinate velocity being equal to c, and then the magnitude can be positive or negative, which corresponds to the velocity being greater than c for positive and less than c for negative. Okay, so that was the length of the full velocity vector. But now let's realise something. That length, which we defined using the metric, is now going to be an invariant quantity. So the length of the full vector, or the full velocity vector, is going to be invariant. So all reference frames are going to have to agree on the length of that vector. And now essentially what this means is that all reference frames can know what the character of your velocity is going to be. Is it going to be a null velocity where your coordinate velocity is the speed of light, or is it one of these cases where you're above or below the speed of light? So we've said that the full velocity is going to have a constant value. It's going to be invariant. What's this value now actually going to be? So let's just remember we wrote down the expression for how we compute the length of the full velocity. Essentially contract two full velocity vectors with the metric. One of these then gets turned into a one form, and then this sum just results in the following formula, so it's minus c squared. Okay, so that's simply the length of our full velocity vector. But now how do we actually go about properly calculating what this length is going to be? Well, we can be fairly sneaky now and use some nice properties of our metric. Essentially the metric is invariant, so this length is going to have to be the same regardless of what frame we're in. So we can make the nice choice. Let's choose to be in the stationary reference frame of this observer. So essentially we're measuring the length of full velocity in your own reference frame. So if you remember, in your own reference frame, you just travel along the time axis, world line, which we said was this c tau, and you don't move in the space direction at all. So essentially, in your own reference frame, your coordinate velocity is always going to be 0. So we can just remove this entirely. And so we see that in our own reference frame, the length of our full velocity vector is going to have to be minus c squared gamma squared. So of course, in our own reference frame, the tangent to our world line is just going to point straight up. And so this is our full velocity vector. just is a vector that points along the time axis, or the proper time axis. And now we've just seen that its length is going to be equal to minus c squared gamma squared. So first of all, we need to now realise, okay, is this a null space-like or a time-like world line? Well, these two quantities, c squared and gamma squared, I haven't actually officially told you, but gamma is just a real number. It's always going to be a real parameter. So this c squared gamma squared is always going to be positive. So minus c squared gamma squared is always going to be negative. And so in our own reference frame, our fall velocity is time-like. And so for all other observers, they're also going to have to agree that our fall velocity is not only time-like, but that it also has this length, c squared gamma squared. Okay, so that's all well and good. We can actually go even slightly further now and realise, remember how I defined gamma, dt by d tau, and remembering that in our own reference frame, t is essentially just tau. So essentially in our own reference frame, dt by d tau is equal to d tau by d tau is equal to 1. And so we can just remove the gamma squared entirely and arrive at the incredibly useful formula, or the realisation that this fall velocity vector, its length, is effectively always fixed to be equal to minus c squared. So I should be absolutely clear what I mean here. I'm saying that we're looking at a fall velocity vector in the reference frame of a stationary particle. So it's effectively just a fall velocity vector describing how a stationary particle moves through space-time. Effectively, they just travel through time at this speed c. And now, using the invariance of the metric, we can measure the length of this vector, find out that it's, well, first of all, it's time-like, and that it has this length which is equal to minus c squared. And now we can use this fact to essentially say that, well, the length of the vector has to be invariant, so in any reference frame, it's always going to have this length minus c squared. Okay, so we can now use this incredibly useful fact that essentially the fall velocity is, well, the terminology we use is we say fall velocity is normalised. Essentially it's normalised to always have a length of c squared. And I should just point out, it's minus c squared because we started with a time-like velocity vector. We could have done this the complete opposite way around and started just by considering a purely space-like vector, and we would arrive at something similar, except that just the magnitude being plus c squared. Okay, but for now let's just work with time-like observers and use the realisation that in your own reference frame you just travel through time, and so your fall velocity, effectively your time velocity, is always constant. But now we should rephrase this as saying that your velocity through space and time, your space-time velocity, it always has a constant magnitude, but it's just going to be able to point in various directions. So I'm going to draw a better picture of this shortly, but just really quickly, if your space-time vector is always fixed to have the same length, it can just kind of point between a space and a time axis. Essentially, this is going to control how much you're moving through space relative to how much you're moving through time. So let's have a better picture of this. Okay, so I'll just remind you that the length of a full velocity vector is always going to be equal to minus c squared. So if you're a real particle, a time-like observer, your full velocity is normalised to have this constant length, minus c squared. So now let's look at how this full velocity is going to appear in a different reference frame to the stationary observer's reference frame. So I'm going to call this X and CT reference frame. And now just for reference, I'll remind you we have our light cone, which we define as being all of the points in Minkowski space which have 0 separation from the origin. And then we have our timelike and spacelike hyperbole. Essentially we have the ds squared negative hyperbole, and then the ds squared positive hyperbole. Okay, so I've just drawn our positive, negative, positive and 0 separation points from the origin. We're going to use these to reference the length of this vector. Okay, so let's just first of all realize if this was our own reference frame, our forward velocity would be just a vector that points straight up and having a length c. Remember that this is kind of the squared length of the vector. But this is now, so the fact that this forward velocity is normalized means that it always is going to have this same length. And so one simple forward velocity vector we can draw is just the forward velocity in your own frame that just points along the time axis. So we can use this to reference the length that this vector is going to have. So it's going to have this length here, which is going to be c. But now what we can now then realize is that, well, we've drawn our points that have constant separation from the origin. This point here has a separation of c. So then all of the points on this red line also have a separation of c. So in Minkowski space, all of the vectors which I'm now drawing all have the same space-time length. So these are all just copies of this forward velocity vector. So all of these are the same forward velocity vector, or they all have the same length, rather. So I should say that these all have the same length. They are different space-time vectors, they just have different components, but those components are going to sum up in the Minkowski way to always give us a length of minus c squared. So now this we can use to realize something incredibly important. Essentially this vertical vector that we've drawn defines a stationary observer, and it essentially has this length of c, which is fixed. And now as this fixed length vector varies throughout the forward light cone, it essentially, it has the same Minkowski length, but now its components are going to start being different. This stationary vector here has no x component, but if we look at this vector here, it does have an x component. So essentially what we're seeing is that as this vector varies throughout this space-time diagram, its length has to be fixed, and that length is then effectively distributed over a space and time component in this way. So now how should we interpret this? Well, a really nice way to interpret this is that essentially, well, this is our stationary observer, and then any vector that points away from the vertical is going to represent a moving observer, an observer that is moving with a coordinate velocity specified by its x component. So this observer here is going to be moving with a much, much faster coordinate velocity than this observer. And now what we can see, essentially what's going to happen is that as we keep tracing out this hyperbola, our arrow is essentially going to tend to, or limit to, this 45-degree light cone vector. Because essentially this u forward velocity has to always, the tip of this arrow has to always lie on this red hyperbola, because it has to have a constant Minkowski distance from the origin. So if we just keep drawing these arrows on and on, all the way up, we're going to eventually, well, we'll never actually quite reach, but we're just going to approach, we're going to limit to the vector lying exactly on this 45-degree light cone. And now the way that we have to interpret this is that essentially this means that our space component of the fall velocity, so the coordinate velocity, we can see it's now effectively being constrained by this fall velocity length to only have the maximum value which would be achieved when the vector lies at 45 degrees, which would correspond to now a velocity of v equals c. And so just the really nice way to think about this is that in your own frame you fix your velocity vector's length, and then any other frame is going to look at that vector and it's just going to be tilted in some way, effectively distributing that purely temporal length over some space and some time components. And this is just going to produce now an increasing velocity in the space coordinate as this fall velocity approaches the light cone. But not only is the space velocity going to increase, the time velocity component we can see is now also increasing. In the stationary frame, this time component is just c up here, but then if we look at a different frame, its time component is significantly larger. And now the way that we should interpret this is that essentially if your fall velocity is not travelling straight upwards, you're essentially, not only are you moving through the space coordinate, you're also moving through the time coordinate at a different rate than you would in your own frame. And so this is how we can now start to interpret the time component of the fall velocity. Remember, it was this thing c gamma. It was the derivative of the time coordinate with respect to the parameter. It's essentially how much is coordinate time varying for every interval of proper time. So in the own reference frame, proper time is coordinate time, and this is just 1. Essentially now if this derivative starts becoming greater than 1, for every infinitesimal d tau, we're going to be increasing a larger amount, dt, and we can see that this is emerging as this vector is moving, or rather its components are changing. We're seeing that this is now producing an increasing space velocity and also an increasing time velocity. And so how this should be now interpreted is that essentially time intervals in your own frame are, well, just we can see from this picture, in your own frame, this is the shortest possible distance along the time axis. And then as we move into moving frames, as this fall velocity increases, this has to be the same length of vector, but the time component has increased. So effectively, this coordinate is saying, in whatever interval d tau, you've increased more in dt than this observer over here, say. So the statement that moving clocks run slow, we can now interpret from this picture as being essentially proper time is the minimum possible time interval that you can elapse. Essentially, it's always the time interval that elapses in your own reference frame. But then as viewed by any other reference frame, that time interval, or your fall velocity vector, is going to not be pointing straight up. It's going to have some other set of components, and the time interval component is going to be much greater than in your stationary frame. So when we start talking about Lorentz transformations and relativistic physical effects, we're going to see much more about this, but just already starting to point it out. In your own reference frame, you elapse a proper time, but then other coordinate systems are going to measure different time intervals for that coordinate time, and we can start to see where this is coming from, and we can kind of intuitively have a nice picture for this due to the fact that our fall velocity is normalized. It always has to kind of lie on this curve here. Okay, so to summarize, we went through and we derived that this fall velocity is always going to have a constant length. Essentially, using the invariance of the length, we can just define it in this fairly simple case where in our own reference frame we can measure its length to be c squared, or the squared length to be c squared rather. And then just simply using this fact and fairly geometric reasoning, we can simply realize that this constraint on the fall velocity is effectively going to control the space and time components. And we've seen how by allowing the fall velocity component in the space direction to increase, effectively looking at the fall velocity of a moving particle through the reference frame, this is not only going to affect how the fall velocity is distributed over the space coordinate, but also how it's distributed over the time coordinate. And so the rates at which you move through time and space are going to differ essentially depending on your fall velocity. So when we start talking about the Lorentz transformations and physical effects, this is going to become much more apparent. But for now, we can just already see that this just quite fundamental feature of the geometry, that these vectors can have negative lengths and that these lengths have to be constant. We can see that constraining our vectors in this way effectively constrains them to lie between this light cone, because essentially now this timelike vector, its length is always fixed to be negative, and so it could never become zero or even positive. And so this now effectively constrains fall velocity to lie between the light cone and to always have a negative length. And so we should realise now that this c upper limit of the coordinate velocity is really just a fundamental feature of the geometry that is effectively constraining the components of our vectors.